So I think it's time for us to. 还有人没回来的，那也。还有一个。厕所吗？还是？
请问一下，这是谁的水壶吗
？OK。
Okay, so I think that we can start the last physics file of this afternoon. So the opponent, please propose your challenge.
We would like to challenge problem 13, spaghetti accelerator.
Problem 13.
With a standard challenge.
Okay. So presenters, please come to the blackboard and write down your name.
fellow competitors. I'm the reporter from Team Excelsior. Today I'm going to report problem number 13, spaghetti accelerator. Here's the problem statement. It reads, when a piece of spaghetti is pushed into a bent tube, small debris of spaghetti may be ejected from the other end of the tube at a surprisingly high speed. So we will investigate this phenomenon. So the main focus for today will be what is the mechanism behind this phenomenon and what relevant parameters will affect the phenomenon. So here will be our outline. The first section will be the phenomenon overview. This is the video of our experiment. And as you can see, it will first bend inside the tube and breaks into a piece and then ejected from the tube in a surprisingly high speed, which is here. And we only capture the highest speed of the graph because we want to minimize the deviation causing by air drag. So as you can see in this chart, the speed of the spaghetti is about 4.5 meters per second. So it is a surprisingly high speed comparing to the pushing speed. So next is about the explanation. For the qualitative explanation, we would like to talk about the emitted speed. So when we push the spaghetti inside a bent tube, it bends due to the normal force right here, which have two contact points. And then the bended spaghetti will store potential energy, which is the elastic potential energy of the spaghetti. Then when the spaghetti normal force exceeded a certain threshold, the spaghetti will break, and when the potential energy transferred to the kinetic energy, the spaghetti will eject. And since the mass of the spaghetti is very little, so the velocity of it will be very big. Then we will calculate the fracture position first. Since we consider the spaghetti inside the tube as a beam, and we can use the deflection equation and the cantilever beam equation to get the connection between the length of the curvature and the connection with tangent theta. So since we doesn't change the theta in each experiment, we can assume that the length of each fracture will roughly be a fixed value. So let's move on to the theory. Since we already know there are only two contact points inside the spaghetti and the tube, we can analyze the force, normal force N1 and N2 by splitting it into two components, which is the x direction and the y direction. And we can get the force, pushing force and theta and phi that can be measured in the force by force meter and tracker, which is right here. The theta is here and the phi is here. So then we will calculate the potential energy inside the spaghetti. Since we can know the potential energy inside the spaghetti will be related to the stress and the strain, we can get this formula. This formula meaning is the potential energy stored by in a unit value, and we interpret the calculation, and we can get this formula. And then because we use the beam theory, so we added the torque of the spaghetti, which is the torque of the normal force N1 and N2's torque, which is A and B, into the calculation, and we separate it to calculate it. So this will be the final potential energy of the bending spaghetti. So Next, we'll move on to the energy transition. When the potential energy minus the friction, the negative work that caused by friction, it will equals to the kinetic energy and the some other energy like fracture energy and the heat. And because we cannot observe the fracture energy in our experiment, so we defined it alpha as the comfort ratio of the energy transition, and which can be determined by the experimental data. So by fixing a line that represents fixing a line on the experimental data, we can get the alpha is about 0.75. So approximately the 25% of the energy is converted into fracture energy and heat energy. So we use the alpha inside every time we calculate the velocity, which is here. And then is our experiment. We first need to measure some of the constants in our experiment. Like, this is the fracture's length. So, as you can see, when the angle theta increases, the length of the spaghetti device will decrease. That's because the greater the bending angle, the greater the normal force exerted by the pipe wall would be. And the pieces will break easier, but the easier here means the distance between the bending place and the where it breaks. And then it's the measurement of friction coefficient. So we measure the friction coefficient by simulating the spaghetti's motion in a tube with two interfaces, which is here and here. Hence, the measured friction coefficient is significantly higher. So that's why the friction coefficient is so high in some conditions. And then it's the measurement of Young's modulus. We measure the Young's modulus by attaching a force gauge to let the spaghetti bend. Here's the connection between the deflection and the force we applied. So our Young's modulus of this spaghetti is about 1.93 gigapascal. So let's move on to the actual experiment. So we have three parameters, which is the bending angle, the pushing force, and the friction coefficient. So first, this is our experimental setup. The bending tube that was mentioned in the problem statement is right here. And it is made of the 3D printed material because we think that will be more accurate if we can fix the angle inside of it. And we made one of the sides clear to let us see through, so we can observe the phenomena easier. And a force key is attached to a moving platform in a constant velocity to give the spaghetti a constant force. And here's the first parameter, which is the pushing force. As you can see, when the pushing force increases, the velocity of the ejected spaghetti will increase. That's because as the bending moment increases, the stored potential energy will be bigger than the negative work of friction. That will cause the pushing speed results to a higher ejection speed. Then is the next parameter, which is the bending angle. As you can see, as the bending angle increases, the velocity of the ejected spaghetti will increase. That's because as the bending moment increases, the curvature ratio will decrease, and that makes the spaghetti store more potential energy according to this formula. And the last parameter is the friction coefficient. as the friction coefficient increases, the negative work done by friction increases, so they will lead to a lower ejection velocity. So, however, we found out that there will be a bigger deviations when the friction coefficient increases. That's because the fracture spaghetti is no longer affected by the normal force, and the coefficient K will be introduced to adjust it more in the situation of bigger friction coefficient. And that is a discussion. So the discussion will be when we focus on the curved part of the spaghetti, the stress on the outer side will dominate the direction tangentially, and the normal force from the tube wall will adjust the direction and causing it to proceed along the tube wall. That is the conclusion. So why does the spaghetti enter a curved tube and shoots out? The reason is the spaghetti bends in and stores potential energy in the bent tube. If the normal force is too strong, it will break and turning into kinetic energy and shoot out. So how do we calculate the emitted force? We first analyze the force, and we calculate the bending moments, and we then define an alpha inside the calculation of energy transition, and then we will have a fitting cover ratio. So this is the end of the presentation. Thank you.
Okay, thank you. So the opponent, please give your question.
I'm the opponent of the variable 2 from page 10. And first one question, can you enter the page 5?
Sorry, wait a second, you can ask another question.
Oh, okay. Here's a question. How did you make your 2?
What?
Make your 2. Your 2.
2. We 3D printed it.
Okay. What is the connection between your theory and your experimental result?
We draw a theory line of the inside our chart, and we found it. We can see the deviation between it is a bit.
Okay, I know. You can turn to the page 5.
Okay.
The question, what is the blue dot below here?
The blue dot is very close to 0. It's because it is still pushing it. And it isn't go over the bending angle.
So when you push the velocity is
Very little. It's not 0, but very little because we push it very slow.
Oh, did you calculate the percentage that the velocity grow?
No, but as you can see, it's very big difference.
Oh, okay. And I'm curious about why is there a lot of dots? Because I think when you do a lot of experiment to make the chart.
No, this is just for one experiment.
Okay, so we can see that the velocity grow up and down. Yeah.
That's because of air resistance, but we didn't consider the dots afterwards.
You didn't consider.
Sorry,
Yes.
time's up. So the opponent, please prepare.
I am the opponent from variable 2. And today I will talk about the spaghetti accelerator and the point I want to discuss with the reporter. First one, phenomenon and setup. The main focus of the reporter is the mechanism behind the phenomenon and relevant parameters that will affect. And the pro of the reporter. She has a great demonstration and clear graphs, clear explanation, great analysis, and great experiment setup. And here are several cons. There's no familiarity with the report and experiment. And here's a theory. Cantor means equation, deflection equation, derivation of potential energy, energy transition, derivation of the ejected velocity, and Gauss modulus. And when the spaghetti bends, it will store more potential energy, and the small mass will have a big velocity. But I'm a little bit curious about how many kinds of potential energy is in her experiment, so I think I will discuss with her later. In terms of experiment, she calculated the energy transfer, and I think it is great. It is a great act because it is important in the experiment. And if we increase the pushing force, it will have higher ejection speed. And if we increase the bending angle, it will have higher ejection speed. Here's the conclusion. We talked about the chart in the page 5, but it seems like I can see that there's a clear growth of the velocity between we push the spaghetti into the tube, and after the spaghetti ejects. So I think I will start from the point of that. I will invite the reporter to go on the stage and let's have a discussion. Oh, please turn to the page 7.
You can ask the question first.
Okay. In page 7, you mentioned that the potential energy will change to another kind of energy, but you didn't mention it clearly. Can you talk about that?
The potential energy will transfer to the kinetic energy of the ejected spaghetti, which is here, of the kinetic energy of the.
So, yeah, it means that potential energy will fully change to the kinetic energy due to the.
No, but we consider it at the energy transition, which is the alpha. We consider it.
So you consider it in the next page.
That includes in the alpha. Yes.
Okay. Turn back. I want to talk about the page. So this one. So here won't be attached with your tube. Won't be
It won't be like crushing to the tube. It will be just slightly just go with the horizontal with the force of it is horizontal with the tube, so we neglected the force loss, like the energy loss of that.
If the spaghetti really have the energy loss between the tube and tube, it will be considered in the energy loss page or energy transfer page.
Yes.
Okay, I know that. Turning to the page 10. Oh, here's the cuter part. Why is the 0 smaller than x and smaller than b, but here?
Oh, we are just calculating the b part, like the force of like the torque of b and the torque here, and will be like considered like we just.
So you didn't clarify the dash here because it is a cuter part because you say that the x can smaller than b, but also can be bigger than B. This is the curious part.
I believe like we made the mistake that this is A and this is B. Sorry, that is the typing error. Sorry.
Turn to the page 19. Stored potential energy. So it's from what energy to store potential energy?
It's the bending of the spaghetti, which we already mentioned in the quantitative explanation.
So is that about the elastic energy?
No, that is when this condition is when the spaghetti still didn't eject. Here is where it ejects, and this is before it ejects.
Before it ejects.
Ejects,
So
and it's still bending inside the tube.
it's still bending.
Yes.
Okay. So it's like the force you give to the tube, and it transforms to the spaghetti, so that thing. So
Yes, but it is the tubes and the normal force between the tube and the spaghetti will give the spaghetti a bending force that makes it store potential energy.
okay. Turn to the page 10. I'm curious about what is N in your formula.
That is the normal force, which is M1 is here and M2 is here. The normal force of the between the spaghetti and the tube.
You calculate the certain data in the
Yes,
experiment.
yes, which is at the force analysis, we split them into like we split the normal force into the y and x components, and we calculated in the
Is there any experiment data to support this?
that is just for like drawing the theory line, and we did have
So you can go to the chart to show me
Okay.
if there is
do
a chart
chart
to show
you want?
the force.
try to show the force.
Yeah.
What do you mean? Like
You say that you calculate, you have to do the experiment to know the force. So I want to know.
but that is for like calculate. We cannot actually measure the normal force between it, but we can calculate it by like the observation of the length of the bending and how it bends inside like the tube, and we actually can.
But you have to calculate the potential energy, and due to that, you have to know the force you give to the spaghetti.
We know the force, but it's like for the theory part. Like, what do you want me to calculate? Like,
Because I think that if you want to know the potential energy, you have to first know the extra force you give to the spaghetti.
yes, but we split the N1 and N2 into different angles, which the two component forces. So it actually the N1 and N2 is inside the formula, but it already been split into like several components inside the, like you can see like the sine, cosine, theta of the phi and.
So it seems like you didn't do the experiment to measure that.
We cannot measure the normal force inside.
Okay, I see. So turn to page 18.
18.
Yeah, how did you draw a line?
We put our experimental data inside the formula, and then we have a lot of little dots, and we attach them together, and it will be the theory line.
Which kind of data you put into the formula? This one or this one?
What do you mean like this one?
To say that you put your experiment data into the formula,
Yes,
and to get the point here.
yes.
So you have to
So
put something.
when we put the potential energy inside the
So
that is a theory line, so it is for like our
theory line. So you use the formula to draw a line, or you calculate the potential energy and the force and give the and know the
velocity. Yes.
and draw a line.
And that is like the idea of like the idea pushing force inside, like we push inside the tube, but the deviations might caused by other things like friction, or we cannot consider like things like energy loss we cannot consider. So this is the ideal.
This one, the red one.
The red line is the ideal theory line that we put the force like the pushing force inside the formula, and we will get this line.
Oh, I didn't understand that because I think that you should put the in my understanding, I think that you calculate the velocity by using the formula, and you put the real data on here. Is that
Yeah.
right?
Yes.
But I'm curious about how did you draw the line?
I draw a line by calculating the
Average?
no. Draw the what line? Like
Red line.
red line is the theory line. It is by putting every different pushing force inside the formula, and it creates a line that is we just put every single
Okay,
pushing
so
line.
you come back the arrow bar here.
Yes, that is the arrow bar.
How the percentage of your arrow bar? How many percentage?
It's from this chart. It's about like maybe under 10 to 20%.
Turn to the page 13. The real length of the spaghetti, how many centimeters or something of your spaghetti?
The full length
Yes.
or the full length will be 10 centimeters, but it will not affect the phenomenon.
Okay.
Yes.
So the first length is here.
Yes.
So this is the arrow bar.
Yes.
How many percentage of it?
It depends on what do you want to. As you can see, it's very small because we already mentioned in our like the calculation of fracture
Okay, so
length. So
can I see any relationship between the dots?
yes, well, when the angle of the tube decrease.
Is there any formula to fit the kind of condition?
This is the
Okay, then we'll move to the next one. Turn to the page 19. Here's four dots. Why is the third one under the line?
it might have been
Okay,
And,
well, push.
like,
well,
when 3D printed, it might be like the direction of the 3D printed. It might be slightly different, so maybe that caused a deviation of that dot. But we think that is linear enough, and there will not be any problem.
So this is
Sorry,
picture again.
sorry, we should stop here. Yeah. So the opponent, please summarize the discussion.
This is this discussion with the reporter. I know several things to talk about. There are some errors in her experiment, and she talked about that, but it is just a guess. So I think it might have to be fulfilled in the future. And another one is that she talked about the energy transition, and I know that it is the force which we give to the tube, and the tube transform to the spaghetti, and the spaghetti have when it's bending, and spaghetti will become bending, and the bending will have the potential force to give the kinetic energy to the debris.
Yeah. Okay. Thank you. So now, reviewer, please raise your question.
I'd like to add the reporter. Please page 5.
Sorry, we can just first
Because I see the point in your graph is about 30 frames per second, so I wanted to ask, do you use slow motion?
Yes, we use a slow motion camera. Like we use a high-speed camera.
But the amount of the point is the same as the normal recording.
That is because when we track the spaghetti, we use like a bigger it's when we track it in tracker, it's what?
Skip some
Yes, we skip some
Okay.
frames.
For page 14. So, do you think the coefficient of friction is a constant for spaghetti?
It won't be it will be a constant in every single material.
Do you change this angle and measure the coefficient of friction for each condition?
We calculated with this formula, and that can
I mean, because if you change the theta, the normal force will be different and the
yes,
coefficient of friction might be different.
and we will consider the theta and when we draw the theory line and the difference of this, like we do 2 experiments, which is when the theta is 45 degrees and 30 degrees.
So the coefficient you got is the same?
Yes.
Okay. For page 21. Because you change the coefficient of friction by change the radius of spaghetti, right?
Radius of spaghetti.
For different radius of spaghetti, the coefficient of friction is different.
Yes.
So will the radius affect the result?
Like, what do you mean? Like the can you say?
Radius is like this.
Yeah, I know, but it will be friction coefficient is related to the theta when the spaghetti will touches the bended tube. So I don't think the ratio will be connected.
What else per reason do you think that may cause energy loss?
First one is the interference between the tube and the spaghetti, because I don't think that it will be perfect that the spaghetti will not to be with the tube beside it.
team, so I'm going to review the problem 13, spaghetti accelerator. This is a problem statement. When a piece of spaghetti is pushed into a bent tube, small debris of spaghetti may be ejected from the other end of the tube at a surprisingly high speed. Investigate this phenomenon. And the key point in this problem is energy transition and energy loss. And this part is the overview of the reporter. For the theory part, they analyze the force, energy transition, and energy loss, and they provide potential energy formula to get the velocity. And for the experiment part, they show the setup and they measure the friction, the coefficient of friction, and how the friction will affect the result. And they change bending angle, the force, and the friction of coefficient. And they mention the error analysis. For the conclusion part, the spaghetti stored potential energy and turning into kinetic energy, and the experiment analyzes the friction, bending angle, and push force. And this part is a remark to the reporter. For the advantages, they detail quantitative research, explain the chart clearly, and they explain the chart clearly. And they provide a comparison between theory and the experiment, and they have created experiment setup and the system. And the experiment is easy to observe. And the suggestion is maybe you can add more videos to show how the reporter do the experiment. And this is a remark to opponents. For advantage, they explain their opinions break, and they notice what is missing on the reporter's theory and the experiment. And for suggestions, you focus too much on the chart, maybe you can turn to other topic at the proper time. Okay, so this is the end of the review. Thank you.
Thank you. So the reporter, please give you a concluding
For
remark.
the concluding remark, we would like to mention that the potential energy will partially transfer into kinetic energy, as we already know, and to clarify the relationship between the bending angle and the velocity is linear enough to fit the theory. And also, the friction coefficient is a constant, as we have already measured in our measurements. And also, the theory line is given by adjusting the variables, which the opponent maybe didn't understand what we are talking about. And also, the deviation is caused by slightly changing in the angle of the tube. The reporter had considered the energy loss, which the opponent think that will be causing because of the friction between the spaghetti and the tube, and we calculated in the energy transition cover ratio, which is the alpha in our report. And we cannot measure the normal force of the spaghetti, but between the spaghetti and the tube, but we can still calculate it by using the formula of force analysis. So this will be the concluding remark of the reporter. Thank you.
Okay, thank you. And now it's time for the jury to raise your questions. Professor Fong.
Question for the opponent, just short answers. Should angular conservation of momentum consider in this case? Should you consider conservation of momentum in this case? Yes or no?
Yes, but we need to minus the friction and other like things that cause energy loss. We can first calculate it by the conserved momentum and then minus the other energy loss.
I think she didn't do that. Although she did the energy conservation, but she didn't go to the next step, which is momentum conservation.
I think the momentum conservation is another way to investigate this phenomenon, but it is enough to investigate by using the energy.
For the reporter, so you study the force dependence of the injection speed. So how do you control the force? I can understand you control the
Oh,
speed.
we control the force by observing the force meter that we push the.
So you control by hand.
No, we will capture when the force meter reaches the amount of force that we want for this.
No, is the force always constant? When in one experiment, is the force always the same or different?
It will increase when the spaghetti is storing potential energy. It will have extremely loss when the spaghetti ejects. So it will be like going up and down.
So you only catch the moment, the force at the moment it breaks.
Yes.
Okay. So question for all of you. So when for the friction coefficient measurement, does the angle of the inclination of the channel affect the coefficient of friction?
I think because the angle affects the normal force, and the normal force may affect the coefficient of friction because of the powder on the surface of the spaghetti, maybe or other reason, but that may cause coefficient of friction is changed.
Yes, it will cause different like the force that causes the spaghetti to bend because with different.
No, my question is, in your measurement, when you have small beads of the spaghetti sliding down the channel, so the question is, if you change the inclination of the channel, does the friction force, the coefficient of friction change with the angle? That's my question.
Since we will consider the angle of it inside when we calculate the effects caused by friction coefficient. So the mu k, which is the friction coefficient, won't change, but we will calculate includes the normal force that.
Okay. So how about the reviewer?
I think it's the coefficient of the friction. It is a property of the thing that that be together. So it is depend on the property of those things. So the angle won't impact on that. So, but I think if we want to make sure the coefficient is more accurate, we can do a lot of different degrees and to have the average of it.
In my opinion, if the normal force change, the coefficient of friction will also change.
Okay, so I think it's almost time, so let's go to the grading. So for the reporter, 78866. And for the opponent, 66757. Last for the reviewer, 46555. So for the reviewer, that I give less than 5 just because you don't discuss, you don't review very much about the discussion part. Yeah, that's the -1. Okay, so I think that's the end of this this afternoon's Biz 5. Then we would like to thank all the 3 teams and all our jury. Thank you very much. Yeah.